I wanted to follow on from last week's discussion on valve authority, where we discussed the difference between sizing 2-port control valves and sizing 3-port control valves. Because I think by now we would all probably agree that we're not sizing 2-port valves properly, and we're probably resulting in lower valve authorities below 0.5, especially as we move closer towards where the pump is. But today I wanted to talk a little bit about what does a poor valve authority do. So when you have low valve authority, 0.2, 0.3, what does it look like? How can we see that in our minds? So through this discussion, we're going to look at what is the relationship between the control valve's equal percentage characteristic and valve authority. Because you need to have good valve authority to have a good equal percentage characteristic. And that is super important, because if you don't have a really nice equal percentage curve, then it means that you do not have a linear transfer of heat from the cooling or heating coils as your valve modulates open. In this little drawing here, this is the characteristic of a heating coil. This actually, as you can see here, it's a radiator heat output as a function of flow rates. This is for a radiator, but a radiator is essentially a coil. So a heating coil or a cooling coil would have a similar sort of characteristic to what we see here. So on the x-axis, we have the flow rate going through the coil, and on the y-axis, we have the heat output in percentage. And the curve looks like this generally. So you can see from this that when you flow water through a heating coil, from 0 to 20% of the designed flow rate through the coil results in a significant increase in heat discharge, in heating capacity in kilowatts. So you could get 60 to 70% of your kilowatts of heating out of a heating coil in the first 20 to 30% flow rate through the coil. And then you can see it's sort of, it might be a little bit linear around here somewhere, and then it sort of tapers off. So as your flow rate is increasing through the coil from 50% through to 100% flow rate, we can see that that does not result in much of a pickup or transfer of heat through the coil and into supply air temperature, where our supply air temperature sensor is. Now in this little drawing on the right here, we have some different valve characteristics. So on the x-axis, we have valve spindle or lift, and actually valve spindle, as most of you probably know, we've got a little mini control valve here. He has the spindle, and the actuator pushes that spindle up and down. So this valve has it's about a 5mm spindle lift. So as your 0 to 100% out of your PI controller is modulating from 0 to 100, and your analog output is going from 0 volts up towards 10 volts, and this spindle is dropping 5mm, that's the spindle lift. I should have thought that through a bit better. Anyway, so back to this little graph here. We have the spindle lift, 0 to 100% travel. In that small valve, that would be 0 to 5mm. On a bigger actuator, on an air handler, it could be 15mm or a 20mm spindle lift. On the y-axis is the valve opening in percentage. So that is, as the valve's opening, the orifice of the valve, as it's opening, getting bigger, and letting more water through. So we can see here that D, a quick opening valve, for example, a butterfly valve or a ball valve, as soon as we crack those valves open 10%, most of the water is going already. As the ball rotates open, a lot of water goes through. As the butterfly disc just turns open a bit, a lot of water goes through. And we can see over here from, like, say, 30% to 100%, you don't get any more flow through it. And that's why we don't use butterfly valves or ball valves for control, because they provide very poor control. We only use it for open and closed applications or shut-off applications. Now, characteristic A over here is a linear characteristic. So if you have a linear control valve, it means that as you open the valve, as you drive, the actuator drives the valve spindle down, we have a proportional opening of the valve's orifice and a proportional water flowing through it. And then finally, we'll just skip past B, characterized V-port. I don't remember using them too much. So characteristic C here is equal percentage. This is the characteristic of an equal percentage valve. And you will all probably know that all of the control valves that we use on coils, whether it's air handling units, heating coils, cooling coils, I was going to say chilled beams, but a lot of people just use open close for chilled beams. So just park chilled beams are a special case. Fan coil, heating cooling valves, VAV, hot water reheat valves. We always use equal percentage valves. Read the data sheet, it always says they're equal percentage. Now, why this is important, and which I'm sure half of you already know, is that when you take this characteristic of a coil and you combine that with the opposite characteristic of a control valve, the resultant is a linear output. So when you mix these two characteristics together, you combine them together, it means that as your PI loop goes from 0 to 100% in your controller, it results in a proportional discharge of heat or coolth through the heating coil or the cooling coil. So as you're watching your supply temperature on the trend and looking at a trend of your PI output, you would see that as your output of your PI loop increases, the supply temperature, in theory, increased proportionally. And that's why equal percentage valves were developed, in my opinion, for the HVAC industry, heating, ventilation, air conditioning, because we mostly control the flow of water through coils in temperature control. So that's a bit of history. A lot of you would know that. That's not anything new. But what we want to go on today is to talk a little bit about how valve authority affects this. Now in this graph is showing us the characteristics of an equal percentage valve relative to changing valve authorities. So we can see over here, when we have a valve authority of 1, we have this shape curve on our equal percentage valve. When we have a valve authority of 0.5, it's a little bit less, it's this curve over here, 0.25. So we can see that as our valve authority of our control valve reduces, it shows that our equal percentage characteristic starts to bend towards a more linear type of shape. So when I said to you before that when you have a valve authority of around 0.25, because we can see at 0.25 from around about 40%, maybe 35%, we almost have this linear transfer all the way up to 100. It's pretty much linear here. Now that means that if we have poor valve authority on our selection, it means that we don't have this equal percentage curve. We have something closer to linear. And when you combine the coil characteristic with a linear transfer from the valve, it means that we end up keeping this characteristic somehow. So this means that as our PR loop opens up to 20%, we've already got 70, 80 percent of heating capacity out of that coil. And that's poor controllability, because our PR loop is expecting us to have 20 to 25% heat discharge. It's not expecting 70, 80% discharge. And this results in control valves starting to hunt. And what normally happens is, because we don't know this is actually happening, you can't see this, we just see we have hunting control valves. So what do? We start to widen the proportional band, try to slow down that hunting, and we widen it and widen. I'm sure a lot of us have done a lot of commissioning. There have been times when you're just sitting there for hours and you widen the proportional band, you just can't get the control loop to stabilize. And it's because you've got the wrong size valve in there. So we sort of tend to end up, whether we realize it or not, we start using software to try and resolve hardware design issues. Now there's a lot more to this, because rangeability of a control valve really comes into play as an issue when you have low valve authorities. The reason why I mentioned that, and I'm not going to go into it now, is just that, once again, like last week's video, we're talking about one small piece of the puzzle. And all I want you guys to take away from today's video is to understand that when you have a poorly sized valve, which is usually a low valve authority, it means that we do not get a good equal percentage characteristic, which means that we do not get a linear transfer of capacity out of our coils from the stroke length of our valve actuators. So guys, if you learned something today or enjoyed this video, please like and subscribe. And if you feel like making a comment, please do that. It would give me some motivation to keep doing this. It's not that easy to try to fit these videos into your normal day job. I do a lot of BMS training, but most of my revenue comes through consulting work, and it's hard to fit these things in. It's a Sunday today, and I'm sitting here in this little room recording these videos. So please support the channel and support me on LinkedIn. And I'll catch you guys next time.